Hello, my name is Yair Schiff, and today I will be presenting our work, DySLIM. This is joint work with Zhong, Jeffrey Parker, Stephan, Volodymyr Kuleshov, Fei Xia, and Leonardo Zepeda-Núñez. In this work, we focus on learning dynamical systems, which are systems in which the time evolution of states is governed by some dynamical model, which we denote here by the calligraphic S. Typically, we have access to the dynamical model only through the observed trajectories, and the goal of learning is to produce a parametric model S theta, which will mimic the time evolution of true dynamics. This is often achieved by minimizing some trajectory matching objective, which penalizes the distance between the predicted and the true states along trajectories in the observed dataset. For chaotic systems, that is those in which nearby states can diverge exponentially, this paradigm can often be insufficient, as even small discrepancies between the learned and the true dynamics can become exaggerated, as the learned model is rolled out for longer trajectories, leading to incorrect or exploded states. Fortunately, many of the systems of interest are ergodic, and they support an invariant measure, denoted here as mu star, on a narrow set of states known as the attractor. This measure is unchanged even under repeated applications of the dynamical model. That is, they are stationary points under the push-forward operation of the true model, which we denote here. The main hypothesis motivating our work is that the learned dynamics also induce an invariant measure, denoted as mu star theta, but that this measure need not coincide with a true invariant measure of the system. In this image, which we will return to in our experiment section, we show two failure modes of this mismatch. In the top, we have a true observed trajectory. In the middle panel, we see a failure where the learned model initially tracks a trajectory, but eventually blows up, or becomes unstable. In the bottom panel, we see that although the predicted trajectory is stable, later states appear to be drawn from a different attractor. We therefore ask whether we can mitigate the instabilities observed by many learning paradigms by moving learned models to the, quote, correct attractor. This leads to the main idea of our work, namely that we do not want to simply minimize the trajectory mismatches, but we want to do so in a manner that preserves the true invariant measure of the system. Despite its appeal, this constrained optimization problem is intractable. And so we convert it to a regularized objective that we will minimize. Namely, we will aim to minimize trajectory mismatches while also minimizing some notion of distance between the learned and the true invariant measures. This leads to the first question, which is what is the right notion of measure distance? Specifically, we want our measure distance to satisfy the following desiderata. It should respect the underlying geometry of the state space. It should admit unbiased and sample-efficient estimation. It should entail convergence properties, meaning that as the distance d goes to 0, the two measures indeed converge. And finally, it should have favorable estimation rates. To satisfy these requirements, we turn to the maximum mean discrepancy, or MMD, introduced in Grenton et al., and denoted in this slide. Importantly, the MMD admits an unbiased estimator that one can compute in polynomial time, where n denotes the batch size, and it entails convergence properties and has sampling error that is independent of the state space dimension. Now, even though we have access to mu star through the observed trajectories in our dataset, it is not at first clear how we can sample from the learned invariant measure, mu star theta. We accomplish this by iterating the learned model for some steps until it reaches mu theta star. We illustrate this with the following caricature. Let the blue region denote the true invariant measure, and the gray one denote the learned one. If we start with the initial conditions sampled from mu star, shown here in red, we can obtain samples from the learned invariant measure, shown here in light blue, by time evolving these points from some sufficiently large number of steps k. To finish the presentation of our method, we also note that the invariance of the measure mu star means that in the infinite sample limit, we can equivalently evaluate the measure distance either with initial conditions or with those from later steps in our trajectories. However, in practice, when estimating d from finite samples, these two quantities will not be equivalent. We illustrate this with the following example. Letting the red points denote the initial conditions sampled from the invariant measure, the green dots represent time evolving these states under the true dynamics, and the yellow dots represent time evolving them under the learned dynamics. We can either estimate the measure distance using the empirical measures of the initial conditions, which we dub unconditional regularization, or by using the empirical measure of the time evolved stage, which we dub conditional regularization, since we are conditioning on the initially sampled true states. Putting this all together results in our proposed DySLIM regularization framework. Starting from any trajectory matching objective shown here as L, we add both the empirical estimate of the unconditional regularizer and the conditional one. In practice, we observe that for different system dimensions, these terms proved more or less useful, and that namely for larger systems, placing larger weight on lambda 2 resulted in a more useful signal for training models. In summary, the benefits of the DySLIM is that it's a framework that does not depend on any prior knowledge of the system, and it can work in conjunction with any popular trajectory matching objective in the literature. Our use of the MMD also means that it is sample efficient and allows us to scale to larger systems, as we will now see. Turning to the experiments, we looked at 3 systems of increasing difficulty and state dimension. For all 3, we observed improvements in both short-term accuracy and long-term stability. Given that our method can be used with any existing objective, our baseline consists of 3 unregularized versions of popular training trajectory matching schemes. Starting with the Lorentz 63 system, we see that in the top graphs, adding DySLIM regularization to any of the baseline objectives improves short-term accuracy with longer decorrelation times, and in the bottom panel, we see that the metrics that compare distributions of true and predicted trajectories are lower when using DySLIM depicted in the orange, even for long-term rollouts. We observe a similar pattern for the larger dimensional Kurvato-Shivasitsky equation. We return to the image on the left, which we previously showed. Looking at the DySLIM regularized trajectories, we see that even with the longer rollouts, we remain in the correct attractor. This pattern is also observed for the largest system, which we examined as well, the Kolmogorov flow, where we see that the unregularized objective collapses to some mode or mean, while our regularized objective is able to stay in the true attractor. To summarize, in this work, we leveraged an important property of many systems of interest, namely the support of an invariant measure. We introduced DySLIM, a scalable and system-agnostic regularized objective, and demonstrated that it improves both the short-term and the long-term stability of learned models. Thank you again to my wonderful collaborators, and thank you all for your interest in our work. To learn more about it, please stop by our poster session or check out the paper and code listed here.